question. What is given? Figure 8.5 shows a capacitor made of two circular plates, each of radius 12 centimeter and separated by a 5 centimeter distance. Okay, so what is the radius of the plate? 12 centimeter, and the distance of separation is 5 centimeter. The capacitor is being charged by an external source which is not shown in the figure, and the charging current is given as 0.15 ampere. So what are they asking us? They are asking to calculate the capacitance and the rate of change of potential difference between the plates. So for the first question, let us write down the inputs. So the radius is equal to 12 centimeters, so that is 0.12 meter, and the distance of separation is equal to 5 millimeter. So we will write it as 5 into 10 to the power of minus 3 meter. Yes, what is the formula for capacitance? Capacitance is epsilon naught A divided by D. Yes, what is epsilon naught value? 8.854 into 10 to the power minus 12 into pi into 0.12 the whole square divided by 5 into 10 to the power minus 3, right? So when you calculate this, we are getting the value to be 80.1 into 10 to the power of minus 12 farad, or we can also write it as 80.1 picofarad, right? So this is the value of capacitance. Now in the same question, the second half is they are asking us to calculate the rate of change of potential difference. So what do we mean by rate of change? So rate of change is with respect to time, isn't it? Generally, if nothing is mentioned, it means with respect to time. So dV by dt. So what is dV by dt? How to calculate that? What is V? What is V? Voltage is Q by C, isn't it? Voltage is Q by C. So since C is not dependent on time, we can write 1 by C into dQ by dt. What is dQ by dt? dQ by dt is the current. So I divided by C. So this equation dV by dt is equal to nothing but I by current by capacitance. What is the current in the question? The current in the question was 0.15 ampere, and capacitance we had calculated just now, so it is 80.1 into 10 power minus 12, right? So when you calculate this, we are getting the value to be 1.875 into 10 to the power of 9 volt per second. Okay, so this is the answer for the first half of the question. Now in the second half, the second subdivision, what are they asking? Obtain the displacement current across the plates, and the third one is Kirchhoff's rule valid at each plate of the capacitor? Explain, right? So first let us do the B question. So in this question, in the B question, what are they asking? They are asking for the displacement current. Now we know very well that displacement current is equal to the conduction current. Displacement current is equal to the conduction current. So from where are we getting this? By the property of continuity. Property of continuity. What is continuity? That the current is continuous, isn't it? So the current cannot suddenly vanish. It is continuous. So what is the conduction current? Conduction current is equal to 0.15 ampere. Therefore, the displacement current is also equal to 0.15 ampere. So this is the answer for the second subdivision. And the third one, what are they saying? Is Kirchhoff's law valid? So yes, definitely the Kirchhoff's law is valid because IC and ID are continuous. Yes or no? Thus, the Kirchhoff's current law is, or in general both the laws, the Kirchhoff's laws is valid at the capacitor plate that's it. Yes, in this question they are asking a parallel plate capacitor made of circular plates, each of radius 6 centimeter and capacitance 100 picofarad. The capacitor is connected to 230 volt AC supply with an angular frequency of 300 radian per second, isn't it? So what are they asking? The question is, what is the RMS value of the conduction current? So first we have to write the input data. In the input data, what is given? This 230 volt, okay, whenever nothing is mentioned, it means that it is the RMS value. Okay, if nothing is mentioned, it is RMS value. And this is angular frequency, and you can see also the unit is radian per second, so this has to be omega. So they are asking what is RMS value of the conduction current. So what is A? IRMS is equal to VRMS divided by XC, that is the capacitive reactance. So VRMS is how much? VRMS is 230 volt, that is what is given. Okay, and XC is equal to omega into C, isn't it? So what is omega? Omega is given as 300 radian per second. So 300 into how much capacitance is there? 100 picofarad, isn't it? So the calculation, once you do it, you will be getting the RMS value of current to be 6.9 microampere. So IRMS is equal to 6.9 microampere. Clear? Now, in the second question, what are they asking? Is the conduction current equal to the displacement current? So one thing you should note here, this is an AC source. Okay, so we know that equation of continuity, the principle of continuity regarding the current is valid for the direct current, but is it valid for alternating current also? So yes, it is definitely valid for alternating current also. Therefore the conduction current is equal to the displacement current. So the answer for the second subdivision is yes, right? And the third subdivision, determine the amplitude of B at a point 3 centimeter from the axis between the plates. So for this, we need to recall something that we learnt in chapter 4. Okay, when a current is passing in a thick wire, let us imagine this capacitor to be a thick wire, right? So the current ID, that is a displacement current, is supposed to be in this manner. Now they are asking, let us say if this is the axis, they are asking at a point 3 centimeter from the axis, what will be the magnetic field? Okay, what will be the magnetic field? So for this type of question, we have a formula. What is a magnetic field? B is equal to mu naught I by 2 pi a square multiplied by r. What does r represent here? R is the distance of the point from the axis, and a is the radius of the thick wire, isn't it? So here the thick wire is nothing but the capacitor. So the capacitor, radius of the capacitor plate will be considered to be the A here, right? So when you substitute, what will you get? And what is this current? This current is the displacement current. So no, because between the plates of the capacitor, we are having the displacement current, right? So B is equal to mu naught. How much is mu naught? 4 pi into 10 to the power of minus 7 divided by 2 pi multiplied by the displacement current is, okay, so we know only the RMS value, we don't know the peak value, so we have to consider the peak value of the displacement current. So that will be equal to root 2 times the IRMS, isn't it? And divided by A. What is A? That is the radius. So the radius is given as 6 centimeters. So 6 into 10 to the power minus 2 multiplied by the whole square multiplied by R. What distance they are asking us to calculate? 3 centimeters. So 3 into 10 to the power minus 2. So when you substitute this, we'll go 2 times. So 2 into 10 power minus 7 into root 2 into how much current did we get? 6.9 into 10 to the power minus 6 into 3 into 10 to the power minus 2 divided by 6 into 6 into 10 to the power minus 2 into 10 to the power minus 2. So once you calculate all this, you are going to get 1.63 into 10 to the power minus 11 Tesla. So this will be the answer for the second question. They are asking what physical quantity is the same for X-ray of wavelength this much, red light of wavelength this much, and radio waves of wavelength this much. So it's pretty obvious that the speed of light in air or vacuum is equal to 3 into 10 to the power 8 meter per second, and since light is an electromagnetic wave and X-rays, red light, radio waves all come under the category of electromagnetic waves, and when these waves are traveling in air or vacuum, their velocity or their speed is going to be same. So the answer for this is the physical quantity is nothing but the speed of the electromagnetic wave. So you can say instead of light, you can call it as the electromagnetic wave. Speed of electromagnetic wave in air or vacuum is constant. Now when these waves enter into a different medium, then their speed will change depending upon the refractive index. Right? Yeah. See, in the next question, they are asking a plane electromagnetic wave travels in vacuum along the z direction, which means z is the direction of propagation. Direction of propagation. Yes. What can you say about the direction of its electric and magnetic field vectors? So, if the wave is traveling along the z direction, then the electric field vector and the magnetic field vector will or have to be along the xy. The electric field vector and the magnetic field vector must be in the xy plane. Only then it can travel along the z direction. Yes. And one more question is asked in the same thing. If the frequency of the wave is 30 megahertz, what is the wavelength? So they have given the frequency and they are asking for wavelength. Now we know that any electromagnetic wave will have the velocity. The speed of electromagnetic wave will be equal to 3 into 10 to the power 8 meter per second, isn't it? So velocity is equal to frequency into lambda. So from this equation we can easily calculate what is its wavelength. What is lambda? Yes. So from this equation lambda is equal to V by mu, and V is equal to 3 into 10 to the power 8. Lambda is equal to V by mu. So the velocity is 3 into 10 power 8 divided by the frequency, which is 30 megahertz. So 30 into 10 to the power 6, right? So finally, what is the answer? 10 meter. Okay. Yeah. So the answer will be 10 meter. So the lambda, the wavelength is 10 meter for this particular electromagnetic wave. Okay. So the next question is like similar to the previous one. A radio can tune into any station of frequency 7.5 megahertz to 12 megahertz band. What is the corresponding wavelength band? So frequency is from this to this range. So they are asking what is the lambda for lambda wavelength band for this particular frequency. So how to calculate lambda? Just now we saw lambda is equal to velocity divided by the frequency, and since all electromagnetic waves are going to have the same velocity, V will be constant. In a particular only in air or vacuum they have the same velocity. Don't mistake it for all medium, right? A particular wave, electromagnetic wave, all electromagnetic waves will have the same velocity in a only air or vacuum, right? Okay. So here lambda 1 is equal to 3 into 10 to the power 8 divided by mu 1. How much is the frequency given? 7.5 megahertz. So mega I can write as 10 power 6. So from this lambda 1, if you calculate, you will be getting as equal to 40 meter. And here lambda 2 will be equal to 3 into 10 power 8 divided by mu 2, which is equal to 12 into 10 to the power 6. So lambda 2 is equal to 25 meter. Yes. So the wavelength band is from 25, or you can say from 40 meter to 25 meter. This is the required answer. So the wavelength band is from 40 meter to 25 meter. Right. Next question is pretty simple. A charged particle oscillates about its mean equilibrium position with a frequency of 10 power 9 hertz. Okay. And what is the frequency of the electromagnetic wave produced by the oscillator? So we know very well, whatever is the frequency of the oscillator, the same frequency is imparted into the electromagnetic wave. So what is the frequency of the electromagnetic wave? The frequency is equal to the same answer, which is 10 power 9 hertz. So the next question, the amplitude of magnetic field part of harmonic electromagnetic wave in vacuum is given as this. Right, 510 nanotesla. What is the amplitude of the electric field part of the wave? So we know very well that the velocity of light, the speed of light is equal to E naught by B naught. So from this equation, what is E naught equal to? E naught is equal to C into B naught. That's it. So E naught is equal to 3 into 10 to the power 8 multiplied by 510 nanotesla. So once you calculate this, you will be getting E naught is equal to 153 Newton per Coulomb, which is the unit of the electric field. That's it. In the next question, suppose that the electric field amplitude of the electromagnetic wave is given as E naught is equal to 120 Newton per Coulomb. They are asking us to find out and the frequency is given as 50 megahertz. So 50 into 10 power 6 hertz. They are asking to find B naught, omega, K and lambda. So one by one we will calculate, and then we have to find the expression for E vector and B vector, right? So what is B naught? Just now we saw one formula. C is equal to E naught by B naught. So B naught will be equal to E naught divided by C. Okay, how much is that? 120 divided by 3 into 10 to the power 8. So that will be equal to 40 into 10 to the power minus 8 Tesla, right? So from this we can also write it like 4 into 10 power minus 7 Tesla, right? And next they are asking omega. What is omega? 2 pi frequency. So 2 into 3.14 into 50 megahertz. So how much is that going to be? That will be equal to 50 megahertz. 50 into 10 power 6. So the final answer will be 3.14 into 10 to the power 8 radian per second. That is a unit for omega. Next is K. So what is K? K is 2 pi by lambda, right? And we don't know lambda, right? So we'll first calculate lambda. Lambda is equal to V by mu. Okay. How much is the speed of light? 3 into 10 power 8 divided by the frequency. How much frequency is given? 50 into 10 to the power 6. So the answer for this one will be equal to 6 meter. Okay. So once you know this, you can calculate K. So K is equal to 2 into 3.14 divided by 6. So the answer for this is 1.05 meter inverse. So there is another equation for K, which is omega by C. You can also use this equation if you want. Okay. Now, finally, they are asking us to find out the equation for E vector and B vector. First, we have to assume any one particular direction for the propagation of the wave. So let us assume that the wave is traveling in the x direction. Okay. This is a traveling wave. So the format for the wave will be E naught into sine kx minus omega t into j cap, and B vector is equal to B naught into sine kx minus omega t into k cap. Now, what does this represent? This j cap represents that the electric field is along the y axis and the magnetic field is along the z axis. Okay, and this represents that the wave is traveling in the positive x direction. Okay, so keeping all this in mind, and we already know the value for k and omega, so we can directly substitute here. We will get E vector is equal to E naught. What was E naught we calculated? E naught is equal to, it's given 120 Newton per Coulomb. So 120 into sine, the value for k is 1.05 into x minus omega. Value for omega is 3.14 into 10 to the power 8 into t. Then it is in j cap. Similarly, B vector is equal to, what is B naught? We calculated B naught 4 into 10 power minus 7 sine 1.05x minus 3.14 into 10 power 8 into t into k cap. So these two are the vector equations for E and B, electric and magnetic fields. And after writing the equations, also mention the unit. So this is Newton per Coulomb and this is Tesla. They have given the terminology used of different parts of the electromagnetic spectrum is given in the book. So they have given about the names, the way we call each part of the electromagnetic spectrum, like the gamma rays, X-rays, radio waves and so on. So we have to use the formula E is equal to h nu and obtain the energy in the terms of electron volt for different parts of the electromagnetic spectrum. Okay, in what way are the different scales of the photons related to the source of the electromagnetic radiation? So in this question they are asking us to find out the energy for every part of the electromagnetic spectrum. So already I think in your textbook the wavelength and the frequency range is given, isn't it? So if we know the wavelength, we can easily calculate the energy. So how do we do that? We know that energy is equal to h nu, isn't it? So nu can be written as velocity by wavelength. Okay, so what is c here? C represents the speed of light and lambda represents the wavelength. And this, if we substitute the values of the Planck's constant 6.634 into 10 to the power minus 34 multiplied by 3 into 10 to the power 8 divided by lambda, okay, we will get an answer in joule. But we want the answer to be in electron volt, isn't it? So what we will do is we will divide this equation by 1.6 into 10 power minus 19. So when you do this, you are going to get 1.24 divided by lambda, 24 into 10 to the power minus 6 electron volt. Okay. Now, if you know the wavelength, you can easily calculate the energy in electron volt by simply dividing the energy by wavelength. Okay, so here I have already given the table. You can see radio waves, the wavelength is 1 meter. So the corresponding energy will be equal to 12.4 into 10 power minus 7 electron volt. We can also write this as 1.24 into 10 power minus 6 electron volt, right? And then you have microwaves in the wavelength range 3 into 10 power minus 3. So the corresponding energy is given. So on we can find out the energy for all the electromagnetic waves. Okay. The last question. In a plane electromagnetic wave, the electric field oscillates sinusoidally at a frequency of 2 into 10 power 10 hertz. So the frequency is given as 2 into 10 to the power 10 hertz. And the amplitude of the electric field is given as 48 volt per meter. You should note that volt per meter is also another unit of electric field apart from Newton per Coulomb. So the next question what they are asking, first one is, what is the wavelength of the wave? So what is the wavelength? Wavelength is nothing but velocity, speed of light divided by frequency, isn't it? So what is the speed of light? 3 into 10 to the power 8 divided by 2 into 10 to the power 10. And therefore we are getting the answer to be 1.5 into 10 to the power minus 2 meter. So this is the wavelength. The next question B, what is the amplitude of the oscillating magnetic field? So they are asking what is B naught, right? So B naught, we know the equation E naught is equal to C is equal to E naught by B naught, right? So from this equation B naught is equal to E naught divided by C. So you substitute the values. B naught is equal to 48 divided by 3 into 10 to the power 8. So we are going to get the answer to be 12 into 10 to the power minus 8 Tesla, or we can also write B naught is equal to 1.2 into 10 to the power minus 7 Tesla. Okay, and finally they are asking us to prove, we have to show that the average energy density of the electric field is equal to the average energy density of the magnetic field. So we can prove this by finding the values, or in general we can prove it for all types of electromagnetic waves. So you can see here that we know two relations. First of all, the first relation is C is equal to E naught by B naught. So this is the first relation. And the second relation is C is equal to 1 by square root of mu naught epsilon naught. I hope you know all this. And when we try to relate the energy density of the electric field, let us calculate what it is. It is half epsilon naught E square. Okay, and the energy density of the magnetic field, that is the energy per unit volume, is half V square by mu naught. Okay, so let us try to get from this equation to this equation so that we can prove that they both are equal. So you can see here UE is equal to half into epsilon naught into E square. What is E from this equation? From this first equation, E is equal to B into C. Okay, so this is E naught by B naught. It can also be written as E by B, right? So B into C the whole square. So what do we get from this? It is equal to half into epsilon naught B square into C square. From this equation, what is C square? C square is equal to 1 by mu naught epsilon naught. So you get UE is equal to half into epsilon naught into 1 by mu naught epsilon naught into B square. So epsilon naught and epsilon naught gets cancelled. You get UE is equal to half B square by mu naught, which is equal to the energy density of the magnetic field. Therefore, they both are equal. So here hence we can say that UE is equal to UB. That's it.